The history of math is our intellectual foundation to understanding science. Science. Beautiful, awesome, wonderful science. It's the creative foundation to our ineffable future. Hi, I'm Gabrielle Burchak, and this is my podcast, Math, Science, History. I often promote my website, mathsciencehistory.com, which I built myself. Of all the hosts that I've been with, my experience with Bluehost has been the best. What I really like about Bluehost is their customer service. It is top-notch, and they are always there to help me. So if you're looking to build a website or you're looking to move to a new host, I highly recommend Bluehost. You can access Bluehost through my affiliate link, which is www.bluehost.com/track TRACK/mathsciencehistory, all one word. Bluehost is fantastic, and they are affordable. It's only $3.95 a month if you sign up for 36 months. So if you do the math, it's $142 to start. And for me, it was the smartest business investment I've ever made. If you are listening to this podcast on April 13th, today is the 395th birthday of the term microscope. As we enter the third week of April in 2020, currently living in survivalist mode, I hope we are all healthy and have the ability to take precautions to stay healthy and avoid getting coronavirus. I just want to send out a huge special thank you to all of our medical workers who selflessly put their lives on the line for all of us. And thank you to all of you amazing people out there delivering boxes and food and dog food and toilet paper to our homes. You are helping us to flatten the curve, and you rock, and you are my heroes. So thank you. Though some people refer to COVID-19 as the invisible enemy, the virus is far from invisible. And we know this because we have microscopic images of the virus, and we've seen the illustration of the virus as that gray fuzzy ball with red spikes. The illustration is a brilliant 3D rendering of what it kind of looks like. The particular illustration that I'm referring to is the gray ball with red spikes. But again, it's just an illustration and not what the virus actually looks like. There was a phenomenal article that I found on Medium written by Robert Britt, and I'm going to post that on my blog, and it'll explain the components of the illustration, and it indicates how much more dangerous this virus is compared to other SARS-related illnesses. In actuality, the virus doesn't really look like a fuzzy gray ball with red spikes. It's actually colorless, and there's another great article that, again, I'll post on my blog at mathsciencehistory.com. The article is from Wired Magazine, and it shows an image of Luke Jerram glass statues that kind of look like the coronavirus. And just as a side note, has nothing to do with coronavirus, Luke Jerram is a British installation artist, and he creates sculptures, large installations, and live art projects. He's a visiting fellow at the Faculty of Health and Applied Sciences at University of West England in Bristol, and like myself, he's colorblind, which is really cool for an artist. So look him up on Google and check out some of his work because he's an amazing artist. Okay, back to the story. So, how do we know what coronavirus looks like? Some of the first images to emerge of the virus were posted by the National Institute of Allergy and Infectious Diseases Rocky Mountain Laboratories in Hamilton, Montana. The images were captured with an electron microscope that scans and transmits the image. After they were able to obtain an image of COVID-19, microscopist Elizabeth Fisher produced images, and then their visual arts medical department, their visual medical arts department colorized the images. The coloring is there so that we can actually see the virus and understand what it looks like. But how did we get this far that we can actually see a virus so clearly and understand its structure? Well, It's all in our history, hence the history and math science history, right? As we all know, microscopes are made from glass, and we have evidence from the eastern Mesopotamian and Egyptian regions of some of the first man-made glass that dates back to 3500 BCE. By 700 BCE, Assyrians would manufacture lenses that could be used as magnifying lenses. One was found in 1850 by Austin Henry Layard in a modern-day Iraq in an area that was formerly called Nimrud. It can be seen at the British Museum in London, and it is called the Nimrud lens. Around 300 BCE, Euclid wrote his work Optics, which covered the geometry of vision and began to set the groundwork for seeing things through glass. This body of work was further studied by many scientists thereafter, including famed mathematicians and scientists Ptolemy, Theon, who was Hypatia's father, and Abu Ali al-Hasan ibn al-Haytham, who is also known as Al-Hazan. By 500 BCE, glass was being manufactured and sold for profit, and by the 2nd century BCE, Chinese were using microscopes made of a lens and a water-filled tube. Then, in the 13th century, Roger Bacon experimented with lenses and suggested that they be used as eyeglasses. This contributed to the development of the microscope. Basically, lenses at this point really only had magnification between 6 and 10 diameters. In the 1590s, the microscope made great progress. A father and son, Zacharias Janssen and his son Hans, who made glasses, had discovered that when several lenses were placed inside of a tube, they could greatly magnify an object. However, the magnification of the microscope was just 9 diameters, but still, this was really groundbreaking. So from this point forward, the developments came quickly. Galileo Galilei was able to use his telescope to see small objects up close. He then developed a compound microscope using a convex and a concave lens that he called the occhiolino, which means little eye. At this time, the word microscope wasn't being used, but I'm going to go ahead and use it so that you know what I'm referring to. Galileo's invention wasn't actually considered a compound microscope because it had a concave lens. In 1622, Cornelius Drebbel presented his invention of the microscope in Rome. It was the Keplerian microscope, which was also one of the first compound microscopes that held a convex objective and a convex eyepiece. Here is where the story gets interesting. In 1622, Drebbel, who lived in London, sent his son-in-law, Giovanni Kuffler, off to sell the microscopes. Kuffler first traveled to France, where he met Nicholas Piresk, and gave him a Keplerian microscope. Then Kuffler traveled to Rome, where he met the Cardinal of Santa Susanna. He gave the Cardinal 2 Keplerians, but never had the chance to explain to the Cardinal how they worked because Kuffler died while in Rome. After Kuffler died, Piresk sent his microscope off to the Cardinal, along with an explanation as to how it works and a description of the things that he observed while using the microscope. However, for some reason, the Cardinal never received the package. Then, in 1624, 2 years later, Galileo had traveled to Rome to meet the Cardinal. While he was in Rome, the Cardinal told him that he needed help trying to get the Keplerian microscope to work. Since Galileo had an idea as to how it worked, he was able to explain Drebbel's invention to the Cardinal without any problem. In the process, Galileo discovered that Drebbel's invention used 2 convex lenses. He figured out how Drebbel's invention worked. So, a few months later, on September 23, 1624, Galileo sent a new occhiolino to Prince Federico Cesi, who was a polymath and who founded the scientific society known as the Accademia delle Scienze. Along with the occhiolino, he included a letter and a description of the lenses that he had to grind down to the correct curvatures. Now, keep in mind, this was in 1624. What's interesting about this particular letter is that it is almost verbatim to the same letter that Drebbel wrote to Piresk in 1622. So, much like today's deleted tweets that never go away, Drebbel's letter resurfaced long after this to lead some historians to question who really invented the compound microscope. Chesi knew he was onto something. On April 13th, 1625, Galileo's friend Giovanni Faber wrote a letter to Chesi about this fascinating tool that could magnify small items. In this letter, Faber referred to it as the microscope, which is derived from the Greek words mikron, which means small, and skopin, which means to look at. Hence, April 13th is the 395th birthday of the word microscope. That same year, Chesi, along with scientist Francesco Stelluti, published their work Apiarium, which included their microscopic observations of 3 bees. It was the first published work that depicted microscopic observations of biological structures. This was the beginning of 395 years of microscope development. In 1665, English physicist Robert Hooke, using his microscope to look at tissue, coined the term cells. Around 1674, Antony van Leeuwenhoek, a Dutch scientist, emerged onto the scene with lenses that he created by grinding and polishing a glass ball into a lens. These magnifying lenses had 270 times the magnification. With his groundbreaking lenses, he was able to see and describe living cells, such as bacteria, blood cells, and yeast. Then, by 1846, Carl Zeiss was mass-producing these microscopes, but his mass production really picked up when physicist Dr. Ernst Abbe became the research director at Zeiss Optical Works. While Abbe was at Zeiss, he created the Abbe sign condition, which is an optical formula that presents the requirements for a lens to satisfy if it is to form a sharp image, free from blurring. Abbe was the brains of this operation, and he set Zeiss up for success, allowing Zeiss to become the dominant microscope manufacturer of the 19th century. In 1869, Mary Somerville published her work, Molecular and Microscopic Science. She wrote this in her 80s. In 1897, American zoologists Catherine Foote and Ella Church Strobel, who worked as research partners in the field, initiated the practice of photographing microscopic research samples. These 2 awesome ladies also created a new technique of observing thin material samples in colder temperatures. Finally, in the 20th century, in 1931, Ernst Ruska and Max Knoll designed and built the first transmission electron microscope, otherwise known as the first TEM. The TEM required electrons, not light, to see an object. So now we're getting into microscopes that can see objects that are as small as an atom. From this point forward, the development of microscopes allowed us to see and analyze microscopic objects that we never thought possible. In 1932, Fritz Zernike developed the phase contrast in illumination that allowed us to image transparent samples. He won the Nobel Prize for this in 1953. In 1957, Marvin Minsky patented the confocal microscope, which uses a scanning pinhole of light to provide a higher resolution in scanned images. In 1967, Erwin Wilhelm Muller created a microscope that was an atom probe and was able to identify the chemical makeup of individual atoms. Kind of cool. In 1972, Godfrey Hounsfield and Alan Cormack developed the first computerized axial tomography CAT scan. In 1981, Gerd Binnig and Heinrich Rohrer developed the first scanning tunneling microscope. 5 years later, in 1986, Binnig, along with Calvin Quate and Christoph Gerber, invented the atomic force microscope. The same year, Ruska, Binnig, and Rohrer jointly won the Nobel Prize in Physics for their work. In 1988, Kingo Ataya invented the electrochemical scanning tunneling microscope. In 1991, the Kelvin probe force microscope was invented. Then, in 2009, Dame Pratibha Ghai made groundbreaking progress with her invention of the in situ atomic resolution environmental transmission electron microscope, known as the ETEM. Her microscope allowed for observations of chemical reactions at an atomic scale. What I just love about her is that she decided not to patent her invention in order to further the advancement of science. So, by 2010, researchers at UCLA were using a cryo-electron microscope and were able to see the atoms of a virus. By the 2010s, we were able to see matter that is smaller than 2 micrometers. It's really exciting that we now live in a time where we have so much amazing technology that can help us see microscopic living matter and help us understand how this virus attacks. So to my point, this virus is not invisible. It's there, and it can be seen by scientists and medical professionals who can then disseminate that information to the public and explain the dangers of this virus that is taking the lives of our loved ones. Thanks to microscopes, there is no confusion as to how this virus is more dangerous than the common flu. There is no questioning as to how this virus gets into our systems and attacks our immune system. In this case, there is nothing more sound and more reliable than science. Scientists are not on a mission to destroy our economy. During this pandemic, our medical professionals and scientists have proven to be the most altruistic group of individuals fighting to save our lives. They are risking their own lives to keep us alive, and they are relying on us to keep them alive by making choices to stay home, stay healthy, and not spread this disease. So, on that note, please trust the scientists who can see this virus and who can find an effective and safe anti-vaccine. And please, stay healthy, my friends. You mean the world to me. Until next week, Carpe Diem. I'm Gabrielle Burchak. This podcast has been brought to you by caffeine. Delicious, wonderful nectar of the gods caffeine. Coffee, tea, coffee candy, you name it. I love it. Thank you for listening to Math Science History. If you like what you are listening to, please remember to subscribe and leave a review. I would really appreciate that. If you are interested in reading more about the history of math and science, please come visit me at mathsciencehistory.com. And while you are there, if you like what you're listening to, please feel free to click on that coffee button and buy me a cup of coffee. Until next week, Carpe Diem.